Okay, everybody, welcome to Physics Today. We're going to talk about work more. We talked about it yesterday, but work we said it can be defined as change in energy. Okay. So, for example, if I have a box here, a 5 kilogram box, if I force on this box, let's say that my B sub naught is 0 here. If I force on that box, am I going to change its energy? Well, first of all, what kind of energy does it have? Is there kinetic energy? No, because there's no velocity, right? Is there potential? Well, you can't tell, but this is a big flat plane. There's no way for it to fall off. So there's no potential. There is chemical, but we're not going to talk about that. But if I force on that box, I'll say that there's no friction too to start off. So this is frictionless right now. If I force on that, is it going to change its energy? Yes, right? It's going to start moving, and then it'll have kinetic energy, which it doesn't at this point. So I could figure out, let's just say I had a force of 10 newtons. I could figure out the acceleration would be 2, right? And if I had a distance, let's say that I did this for 20 meters, I could figure out what the velocity is using the square root of 2ax. Do you agree? But there's another way to do it. It's using the energies. But before we use the energies, we have to explain this new formula, and that's the work formula. Okay, so here's the new formula. Work is equal to a force that's applied to an object parallel to the object's displacement. Okay, so here's the formula on the board. So in this case, this force here is going in that direction. The displacement that we apply the force over is going to be 20 meters. So I have a mathematical description for work here. So I can say my work is equal to force times the parallel displacement. In this case, it's 10 times 20. In this case, it's 200 joules. So if it's a change in energy, it's got to have the same label. So energy is in joules, so work is in joules. Now what energy did I change this into? Kinetic, right? So that equals kinetic energy, which equals 1/2 mv squared. We can figure out our v then at the end of this work is the square root of 400 times 5. And that would be my velocity at the end of this work period. Okay, now keep in mind, energy and work is directionless, it's vector, so this doesn't give us a direction like the kinematic equations do, but it's a little bit easier to do some of these problems with. Any questions on that? So in this case, there's no friction, so all the work was put into a change in the kinetic energy. Now, if this thing would have been moving already, I could have forced in the opposite direction and taken away from kinetic energy. But in this case, there was no initial velocity, so everything that I put into it was realized in an increase in the kinetic energy. Well, this whole idea here is coined the net work kinetic energy theorem. Okay, now I have seen it called just the work kinetic energy theorem with the net being implied. So what happens if I have, net work would be after all the positives and negatives are added together, what do you have in the end? That's what net means, right? Versus like the gross. So let's talk about a situation where we have some negatives. Which if we're talking negative, we must be talking friction if my velocity is 0 in the beginning. So let's say that I have the same 5 kilogram mass, and we'll say that I'm tugging on this with 100 newtons of tension, and I do that over a distance of 20 meters again. But this time I have a coefficient that's equal to 0.333. So which way is that friction going to be forcing on this box? I'll say also my V sub naught is 0. Which way? In what direction? Left or right? Left, right? So there'll be the force in that direction, but that's going to be applied over that same distance, or displacement. If you look at the formula, work of friction would be the force. And now if I say that this direction here is positive, then that force would be in the negative direction, in this case. Do you agree with that? Because if I'm deeming this a positive direction, then this would be the opposite or negative. And then the displacement here is 20, which is, the displacement that's occurring is still in the positive direction. So what do you see? Our work of friction then ends up being a negative number. Okay? So like I said, there's no real negative in the vector sense, but this would be taking away from this other energy. Okay? So we want to talk about this kind of in this big equation form. It would be the kinetic energy is equal to the work that's done by the tension minus the work of friction. And it's a minus, we know, in this case because it's going to be in the opposite direction of the displacement, the forces. Okay? So the increase in kinetic energy would be the force parallel to displacement. That force is the tension force. Minus mu and d, kind of like our university. Okay? But the kinetic energy then would be the applied force of tension, which we have as 100 newtons over 20 meters, minus my mu is 0.333. The normal is 50 newtons, right? So it's 50, and the displacement is 20. So my kinetic energy increase is quite a bit. 1,666.67 joules. And let's say you wanted to figure out what the actual velocity is. You know, so this is change in kinetic, and since there was no kinetic in the beginning because we had a 0 velocity, then the change in velocity would be equal, or not equal to, but a direct correlation to the change in kinetic energy. So we would set this equal to 1/2 mv squared and solve for velocity, and we could find out what our new velocity is. Okay, so let's look at another situation here. Let's say I have a box of 50 kilograms. Let's say I have, I better move this around a little bit. Say I have a tension here of 500 newtons, We'll say that my V sub naught is 0 again. And I have a coefficient of 0.111. Okay, so the question here is going to be, again, what's the velocity at the end of the situation? So my formula would be my kinetic in the end is equal to the work provided by my tension minus the work that friction does. You agree with that? Okay. So my kinetic energy is going to be, so here's the new thing. Remember, our formula is work is equal to a force that's parallel to a displacement. Okay, so as you can see, the tension is not parallel, right? So we got I forgot to put in a angle here. We'll say that this is 30 degrees. But this would be the part that's parallel to the displacements. So if I'm displacing this thing, let's say 10 meters, with my force of tension, I can't use the full 500. So my force parallel to displacements, is this number right here. What's the cosine of 30 times 500? Is that 433? So we'll say 433, which is this part right here, 433 times 10 minus the work of friction. So the friction would be mu nd. So in this case it's 0.111. But the normal here isn't the 500, right? Because the tension is pulling up on that box. So it's 500 minus this piece here, which is 250 newtons. The sine 30 times 500 is 250. So the normal then is 500 minus 250 because it's getting help by the tension. So the normal in this case is 250. And that friction works over the same 10 meters. So my kinetic energy would be 4,330 minus 277.5. And so the difference between those two numbers would be what I have left over that equals kinetic energy. And if I was going to solve for my velocity, then I take this, and that'd be equal to 1/2 mv squared, and I could just solve for my velocity. Okay, let's look at a situation here. Let's say I got a 5 kilogram box. Let's say my initial velocity is 10 meters per second. Let's say I'm trying to slow this thing down, so I apply 4 newtons, and let's say that this is frictionless. But I'm pushing on this with 4 newtons, and I do that over 10 meters. So my kinetic energy then is equal to my initial kinetic energy minus my work of the push. So in this case, it's 1/2 5, that's mass, times 100 minus the work is my force of 4 newtons over 10 meters. I'm going to be slowing this thing down, right, because I'm pushing on it. So my new kinetic energy is going to be 210 joules. Okay? My final kinetic energy is 210 joules. And if I wanted to figure out my velocity, I just set that equal to 1/2 mv squared. It gives you my new velocity. So this stuff is a little easier than the kinematic equations. Okay, so now we've got a 5 kilogram mass sitting on a ramp that's 10 meters high with a 30-degree angle. So this is answering some of the questions that you had on the homework I was due for today. Okay, so we'll just say that I have in the end, I have a velocity of 10 meters per second. Okay, so the question is here, is there friction? And if there is, what was the force of friction? So the first question you need to answer is, what is my potential at the top? My potential at the top is mgh. And in this case, it would be 5 times 10 times 10, which is 500. 500 joules is my total potential energy at the top. Because I have my height of 10, 5 kilograms, and my little g is 10. So the question is, did I realize all that energy at the bottom? So my kinetic energy at the bottom here then is 1/2 mv squared. In this case, 1/2 times 5 times 100, which is only 250 joules. So looking at these two numbers, I can see that I lost some mechanical energy. Oh, what do you lose mechanical energy to? Well, you lose it to the heat, or the increased movement of the particles due to friction in this case. So, if I'm trying to figure out the work of friction, well, the work of friction is going to be equal to my potential at the top minus my kinetic at the bottom. Or you might do kinetic minus potential and then get a negative work. Doesn't matter as long as you understand what's happening here. I'm losing my mechanical energy. So in this case, my work of friction is going to be 250, right? Because I should have 500 realized if there's no friction, but I only realized 250, therefore I lost energy due to work, and this is the amount of energy that I lost right here. Okay? So now the question is, what is the force of friction? Well, first of all, in what direction is the force of friction going to be in? Well, it's going to be in this direction, right? Because it's slowing it down. It's impeding the motion. So, the work of friction here, we know is 250. I'm going to erase that for right now. So we know that work is equal to force parallel to displacement. And we know in this case our work is 250. And this is what we're looking for, the force. Well, we're actually looking for displacement too. We don't have that. But if you look at your relationship between the angle and this side of that triangle, it's a sine function, right? So this distance here then is going to be 20 meters. Because we know the sine of 30 is half, and if our height is 10, then double that would be 20. You can do your SOHCAHTOA stuff to figure that out. So this displacement that's parallel to this force is going to be 20. So the force of friction then is 250 divided by 20, or 12.5 newtons. Do you have any questions? Okay, well that should help you do your homework. We still have 20 minutes to work in class.